Hello everyone, my name is Mo'min and I'm on the MT Smart Tools team. Today I'm presenting our senior design project. Really quickly, here are all the other members that worked alongside me to complete this project this semester. So what was our project? Well, we were tasked with creating a free fall detection device for Milwaukee Tools. Milwaukee Tools wanted this free fall detection device because a lot of their handheld power tools with lock-on triggers actually remain powered on when they're dropped, and this could cause injury to the user. So what were the specifications of the device that we had to create? Well, it had to cost us $10. It had to be incredibly accurate, such that regular usage of the device does not detect it as a drop. Only actual drops need to be seen as drops. Putting the tool on the table, that's not a drop. Aggressively putting it down on the table, that's not a drop. When waving your arm while holding the tool, that's not a drop. And our algorithm had to account for all these cases. And it had to do this while also detecting the fault in less than half a second. Additionally, it had to be enclosed in an enclosure that's able to withstand a 3-foot drop. So what is the hardware we kind of decided to use to solve this problem? We use our PIC32 microcontroller. This has a ARM Cortex M0 Plus core on it. We also use the ICM4260 IMU, which is a 6-axis motion tracking device. It combines a 3-axis gyroscope and a 3-axis accelerometer. And we use our MPLAB Snap debugger to flash code onto our microcontroller. So how do all these hardware components connect it together? Well, you kind of see right here we have our IMU sending data to our microcontroller, which would then use our algorithm to analyze the data from the IMU. If a fall is detected, it would then toggle the LED. And as you can see, the device is powered by a battery. Here's a little more detailed schematic of the device which we were creating. After creating the schematic and creating the circuit, the next step was to create the firmware. To do that, we relied on the tools provided by the manufacturer of the microcontroller. We used their MPLAB IDE and their MPLAB Harmony tool. Their MPLAB Harmony tool allowed us to use a GUI to configure different pins on the MCU and then generate APIs for these pins and interact with the pins using those abstracted APIs. And we use this to use the I2C bus to send data to the IMU. We use it to configure to toggle the LED, and that was what we used throughout our entire firmware development. Once we had this firmware up and running, we kind of wanted to work on an algorithm to make sense of the data coming from the IMU. So to do this, we use a threshold-based algorithm. And this just used like a minimum and a maximum acceleration bound and a maximum angular velocity bound to detect when a fall had occurred. But in order to generate these bounds, we actually needed a lot of data from our IMU to do this. So we performed over 100 trials to get the data. And our trials were quite varied. It included regular usage of the device. It included dropping the device, and it included aggressively placing the device down on the table. And we then ran it through our algorithm to generate bounds which are able to detect a fall only when a fall actually occurs and not detect the fall in other cases like aggressively putting it down or waving your arm while using the tool. And we got this working with pretty high accuracy. And once we kind of had all this up and running, we wanted to put our entire electrical components on a PCB. And as you can see right here, we have a 6x6 centimeter PCB. The PCB at the bottom right was printed in the mechanical engineering lab. One on the left, at the bottom left, was printed by a manufacturer. The main challenge here was that due to a lack of time, we actually had to solder a lot of these components by hand. And many of these components are incredibly small, which made the soldering incredibly difficult. But once we had this PCB running, we had to protect this PCB so that it's able to survive the fall that it's meant to detect. And so you kind of see over here, we have this packaging right here. We included some foam plastic around the PCB. We had some hot glue around the corners and the edges of our box to lessen the impact on the PCB. Additionally, we added some gaps on the top to actually see the LED when it turns on. The box was slightly larger than the PCB, which was in it.
Now, this is our final free fall detection device. I'm going to shake it. The LED doesn't light up. I'm going to move it up and down by manually. It doesn't light up. When I drop it, the LED lights up. When I drop it on the other side, it also lights up. And if we smash it hard on the table, it also doesn't light up.
So what were the main challenges we faced during this project? The main challenge was the global chip shortage, which really limited what microcontrollers we can buy, what IMUs we can buy, and what components we could buy. We had to rely a lot on the Hive Senior Design Lab and our previous ECE courses for electronic components. The other main challenge was the device had to be battery powered, which meant we had to be very cognizant of how much power our device was consuming. If it consumed too much power, the device would be essentially useless. Given all these challenges, what have we managed to accomplish? Well, we created a free fall detection algorithm with a 94% accuracy. It was able to eject the fall within half a second. The enclosure was sturdy enough to withstand multiple 3-foot drops. The power consumption was quite low, and all this was done at about $5.80 per device, which is much lower than the $10 target we had placed in the specifications. So how can this project be improved in the future? Well, there are still some firmware changes that can be done to lower power consumption. The PCB could be made more durable by only using surface-mounted components. As I said earlier, due to the global chip shortage, we didn't really have time to wait on all the surface-mounted components to arrive. We could generate more data to improve our algorithm accuracy, and we could kind of improve our packaging to make it more lightweight and a little more stable. Thank you for listening to our presentation.